All right, we're going to get to some examples where we see how to calculate the energy of a photon that causes an electron to transition from one energy level to the next, and also calculate the frequencies and wavelengths associated with those photons. So 1A through F are going to be very similar examples that show basically the most you'll ever have to do. Determine the energy and frequency, and I'm going to add this in, and the type of radiation of the photons given off by electrons making the following energy level transitions. So we're going to start off with a hydrogen atom and an electron in that hydrogen atom making a transition from n equals 3 to n equals 1. We want to know how much energy that photon will have. Now we know that when the atom is emitted, or when the electron is emitted, the energy of that when the electron transitions between energy levels, the energy of the photon that is emitted will just have the same energy as the difference in energy levels. This says hydrogen from n equals 3 to n equals 1, so we need to take a look at the energy level diagram for hydrogen. N equals 3 is at an energy level of negative 1.51 eV. N equals 1 is at an energy level of negative 13.6 eV. We need the difference between those. It's not just going to be negative 1.51 because that's n equals 3, or negative 13.6 because that's n equals 1. These really have no value other than we need to know the difference between the two of those. So here's how we start. We say that the energy of the photon that's released is equal to the initial energy minus the final energy. It starts off at negative 1.51 eV minus a negative 13.6 eV. The energy of the photon that is given off is therefore 12.09 eV, electron volts. That's part of our answer. Now, if we want to know the frequency of that photon, the frequency of light, which can help us determine the type of light, then we need to use this equation. E photon equals h times F. However, the energy must be in joules, so before we do anything else, we need to convert this to joules. 12.09 eV, we want to convert from eV to joules, so I need to set up my fraction like that. I go to the front of the reference table, and I see that 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. Okay, kind of squishing my writing in there, but that means I'm going to take this 12.09, multiply by 1.6 times 10 to the negative 19th. I end up with 1.9344 times 10 to the negative 18th joules. That can get plugged into this equation. The energy of a photon is equal to h times F. The energy of the photon is 1.9344 times 10 to the negative 18th joules. H is Planck's constant. Planck's constant is given on the reference tables, 6.63 times 10 to the negative 34th joules times seconds. Times F. We solve for F. Oh dear. Hit a button too quick. There we go. F is 2.92 times 10 to the 15th hertz. That's the frequency. In order to determine the type of radiation, we go to page 2, the electromagnetic spectrum chart. We look for times 10 to the 15th hertz. So the upper bound of violet is 7.89 times 10 to the 14th, so this clearly isn't visible light. This is between 10 to the 15th and 10 to the 16th. It must be ultraviolet. There we go. So we found out that in this energy level transition, if an electron falls from n equals 3 to n equals 1, it releases light with this energy and this frequency. Therefore, it is this type of light. So again, we found the difference in energy levels, converted that from electron volts to joules, and then used E equals HF, found the frequency, and used the chart to find the type of light. I'm going to do the same thing for B. What if an electron in a hydrogen atom falls from n equals 5 to n equals 2? We start off the same way. n equals 5, be careful, is negative 0.54 eV. The final, at n equals 2, is negative 3.4 eV. The energy of the photon that is given off is the difference between those energy levels, 2.86 eV. We're going to convert that to joules. Once we have the answer in joules, we use the equation that relates energy and frequency for a photon. .9 times 10 to the 14th hertz. We go to our chart. That's clearly lower than violet and greater than the lower bound for red, so that must be in the visible light, 6.9. So let's see, that's between these two boundaries for violet, so it must be violet light. I'm going to do C through F, but it's pretty much the same process, so please follow along. Or even better, you could pause this, do these on your own, and then check to see that I get the same answers as you. That's UV light. Now we're going to go on to mercury. Should probably circle these energies since that's the other thing we're looking for. Okay, 7.87 times 10 to the 14th. Just outside the upper bound for violet, so this must be ultraviolet light. All right, this is also above violet, so it must be ultraviolet. And the last one. Okay, last one, 5.19 times 10 to the 14th. We see that that's just inside the upper range for yellow, so it's kind of starting to look green. We would still classify this as yellow light. So to sum up, if you're given an energy level transition, it's usually pretty easy to figure out what the energy is of the photon that's given off. You can convert that energy into joules. Then you can use this equation to find the frequency, and then you can use the chart to find what type of light it is. Let's look at some other examples. In a hydrogen atom, an electron absorbs a photon and jumps up from the n equals 1 state to the n equals 4 state. What was the energy of the photon that was absorbed? So remember, I said for absorbed, we're going to use this equation. E photon equals EF minus EI. And the key here is this will allow the answer to be positive. If it so EF, the final energy state, is n equals 4. That looks to me like it's negative 0.85 electron volts. Remember, electron volt is a tiny unit of energy, much smaller than a joule. The initial is n equals 1, that's negative 13.6. So we find the difference between those. We get that the energy of the photon that it absorbed was 12.75 eV. Okay, and again, notice that's the difference between the energy levels. The energy levels themselves aren't all that important. It's the differences that are important. If the photon if it had 12.74 or 12.76, then nothing would have happened. It has to be the exact right amount. If the electron then falls to the n equals 2 state, what is the frequency of light that will be emitted? Well, so now we're emitting a photon, so we go back to EI minus EF. The initial state is n equals 4. We know that that's negative 0.85 eV minus a negative, n equals 2 state is negative 3.4 eV. So the energy of that photon is 2.55 eV. We want to know the frequency of light that will be emitted, so we use this equation, but first we need to convert to joules. So 2.55 eV, 1 eV is 1.6 times 10 to the negative 19th joules. That would be 4.08 times 10 to the negative 19th joules. Plug in Planck's constant, divide by that to find the frequency. I get 6.15 times 10 to the 14th hertz. And just for good measure, we'll figure out what type of light that is. We go to the chart, we read the frequency. Times 10 to the 14th is usually, but not always, visible light. 6.15 is between the two boundaries for blue, so this ends up being blue light. Blue light is what is released in that atomic electron transition. Okay, a 6 electron volt photon approaches an electron in the ground state of a mercury atom. To which energy level will the electron transition? So we look at mercury. We see the ground state is negative 10.38. If it's a 6 electron volt photon, that means if we add 6 to that, it should go up to whatever energy level has an energy level reading of negative 4.38. None of them have that. So what happens? Nothing. It doesn't go to any energy level. It stays in the ground state because no energy level is exactly 6 electron volts higher. Has to be exact. All right, a second photon comes along and causes the electron to transition to the I energy level. How much energy did this photon have? Since it's an absorbed photon, we use this equation. The final energy level is the I energy level. That's negative 1.56 eV. Minus a negative, where did it start? Let's see, ground state, so negative 10.38. The energy of the photon must have been 8.82 electron volts to get absorbed and go up to that energy level. We want to know what the wavelength of this photon is and what type of radiation it was. First thing we need to do is convert to joules, 8.82 eV. Let's see, 1 eV, 1.6 times 10 to the negative 19th joules. .4112 times 10 to the negative 18th joules. And since we're looking for a wavelength, we're going to use this equation. Energy of the photon. We know it equals HF, but we could also say it equals HC over lambda. We multiply both sides by lambda to get lambda over here, then we divide by the energy of the photon. I get this. Lambda must be equal to Planck's constant, 6.63 times 10 to the negative 34 joules times seconds, times the speed of light, which is 3 times 10 to the 8th meters per second, divided by the energy of the photon, which we divided by over here, which is 1.411 2 times 10 to the negative 18th joules. We get that the wavelength should be, let's see, 1, 2, 3, 4, 5, 6, 7, 1.41 times 10 to the negative 7th meters. That's the wavelength. However, I would strongly caution against trying to find the what type of radiation it is based on this. Because if you look at times 10 to the 7th, it looks like it could be ultraviolet, visible, or maybe even a little tiny bit infrared if you're just looking at something times 10 to the 7th. We need to find the frequency. We can do that using V equals F lambda. We know the speed of this light. It's light, so it's 3 times 10 to the 8th meters per second equals the frequency times what we just found. So the frequency must be 2.13 times 10 to the 15th hertz, and anything times 10 to the 15th is generally going to be ultraviolet. Okay, so again, don't try to use this chart to figure out the type of radiation unless you know the frequency. If you only have the wavelength, convert to the frequency. 3 more. An electron in the n equals 3 state can release photons of what energies? So n equals 3 means it's hydrogen. If the electron's up here, how does it release energy? How does it release photons or emit photons? It falls down. Now it can do this in one of two ways. It could either fall from n equals 3 all the way to n equals 1, or it can go from n equals 3 to n equals 2, and then from n equals 2 to n equals 1. 2 paths to the ground state, I should say. Let's do the direct one first. If it goes from n equals 3 to n equals 1, what energy does it release? Well, E photon equals EI minus EF. N equals 3 is the energy state with a level of negative 1.51 eV minus a negative ground state, negative 13.6. The energy of the released photon is 12.09 eV. That's one possibility. What if, on the other hand, it goes from n equals 3 to n equals 2 and then to n equals 1? Let's just worry about the first part, n equals 3 to n equals 2. EI minus EF. Well, it's starting off in the same place as over here, so that's negative 1.51 eV minus n equals 2 is negative 3.40. The first photon that's released when it's halfway down, or I shouldn't really say halfway down, but when it's one energy level down, has an energy of 1.89 eV. And we could find the frequencies of all these, but it didn't ask us to. And then the second one, to go from n equals 2 to n equals 1, starts off at negative 3.4 eV minus a negative 13.6 eV, because that's the final, it's at ground state. (10.2 eV is the final photon released. So we can see photons of 3 different energy levels. And it makes sense, since it's starting in the same place, ending in the same place, the total energy released is going to be the same either way, whether it's released all at once or in 2 spurts, okay? 2 different photons. Add these photon energies together, and you get this. Kind of makes sense. All right, how much kinetic energy will an electron in the ground state of hydrogen have if it absorbs a photon of 15 eV? Well, you might look at hydrogen and say, okay, well, the ground state is negative 13.6. There's nothing that's exactly 15 eV higher, so it doesn't happen. But notice that 15 electron volts is enough to make it ionize. That's what's going to happen here. So, if more than enough energy to ionize, whatever is left over becomes kinetic energy. Since it takes, now to ionize, we need to get it to this level here with 0 eV. If it starts off with negative 13.6 electron volts of energy, we need to give it 13.6 to get it to the base ionization level. Since it takes 13.6 eV of energy to ionize, then 15 eV, that's the energy of the photon, minus 13.6, the energy to ionize, equals 1.4 electron volts of kinetic energy. That's how much kinetic energy it has left over. And then finally, real basic one, what is the minimum energy needed to ionize a mercury atom that is in the C energy state? C energy state is negative 5.52 electron volts. Ionization happens at 0. So since the energy of C is negative 5.52 eV, needs positive 5.52 electron volts of energy to ionize. Okay, very simple. Atomic transitions are honestly one of my favorite topics of the year because you get to see a fairly complex thing that's working, but it has applications in a lot of places. We use emissions spectra everywhere. We use what light is given off by certain transitions to determine what different things are made out of. It's really, really neat. Remember, the keys are to figure out the energy level difference. The energy levels themselves are not all that important. It's the energy level difference that matters. To make sure to convert from electron volts to joules, and then to use this equation right here, the energy of the photon equals Planck's constant times a frequency, to figure out the frequency, and from that we can figure out what type of light is given off, and therefore figure out what sort of material that we have, since all energy level diagrams, or all energy levels for all the different elements and all the different combinations of elements are completely different. That's the most math we're going to do in this modern physics unit. Next, I believe we will be talking about the nucleus and what is inside. Talk to you later.